All right, so today's plan is kind of do some review, go over probably mainly hypothesis testing examples, but really any questions that you would have, we could kind of go over. So I'll kind of mention a couple things before I field questions. One thing, I had someone reach out and said a couple people were having some confusion. I'm pretty sure I said it, but just in case, that connect assignment that's up there, it's just practice problems, right? It's not worth any points in terms of your grade. It's just put some additional problems up there if you want some confidence interval hypothesis testing questions to kind of work through on top of the ones in the practice exam or anything that we do in class. So it's just for practice. I'll start to kind of get those Excels graded throughout the week, although the grading of the Excels and the second exam may all be done kind of right at the same time. I will put up a answer key to that Excel assignment. I don't know how much that's really, not asking Excel specific questions on the exam, but just in case you had some questions over the kind of non-Excel parts of that, I'll get that answer key up this afternoon. Other than that, kind of the exam, I kind of was going back and forth. And so I think what I'm going to end up doing is kind of just have it set for 20 kind of multiple choice questions. The last 4 I could make short answer, although after going back and forth, I think leaving them completely short answer and giving partial credit would be not as beneficial as seeing 4 different answers where I'm giving you some that you can rule out right away, or at least giving you a direction in terms of kind of what you should be doing for that problem. So kind of just 20 multiple choice. I also want kind of time not to be an issue here. So I would say kind of the breakdown, if you're looking at those practice exams, they might have a few more hypothesis testing questions than this one will. So there's probably only going to be about 7 or 8 hypothesis testing questions. Actually, I think there's exactly 8. And then, maybe 3 or 4 kind of related to confidence intervals. And then the other 8 is just kind of thinking about the uniform distribution, a regular normally distributed variable, and then kind of what the distribution of sample means might look like. So it'll look very similar to the practice exams in terms of the content, with the exception we said last week, no critical value stuff, which kind of cut down a couple of the questions from the hypothesis testing. But those should still be your best resource when you're studying for this exam. Okay. I mentioned the formula sheets up there on Canvas, so we'll kind of take a look at that here today. And I'll maybe even start out kind of pointing some things out with what equations are what. Other than that, are any questions logistically about the exam for me before I kind of jump into some stuff? Okay, so I'll try to get here a little bit earlier. We'll kind of get started a little bit earlier on Wednesday. That way time is not as much of an issue. But to start out with this formula sheet, if I was kind of going through it, so, this first part is just reminding us that anytime we have a variance, we can find the standard deviation by simply taking the square root. Hopefully that's pretty old hat right now. This next set of equations is going to be for our uniform distribution. Okay? So you've got, kind of the height of your uniform distribution, how you find the probability being in between any 2 values, A and B, for a uniform distribution, the mean, and the variance equations if you have a uniformly distributed variable. The next kind of set of equations is just when we had a normally distributed variable, we were looking, turning things into z values. We're using that inverse transformation. And then our next set was, okay, now that we have this normally distributed variable, what do we know about the distribution of our sample means? Well, they'll also be normally distributed as long as the sample size is over 30. So we've kind of got the calculation for the variance of we've got the calculation for the variance of our sample means, whether or not we're using a population or a sample variance. And kind of a reminder for what the standard deviation is, just the square root of that. I even remind you, if I don't directly give you kind of p hat, like this was the idea of, 72 out of 200 people do whatever we're looking for, right? So that number of successes over the number of trials gives you that sample proportion. We then had the variance for our sample proportions. Come up here. This is how we kind of turn sample means and sample proportions into z values. We then had our confidence intervals, 3 different types. One where we're building a confidence interval for a population mean based around our sample mean. When we were given a known population variance, we then had the confidence interval for our population mean built around our sample mean, but we only have the sample variance, which meant everything's the same, but we have to use that student t distribution. And then building a confidence interval for where the true population proportion is, that's centered around our sample proportion. And then we have the same types of examples for hypothesis testing. Here's our 3 test statistic equations, right, for hypothesis testing for those 3 types of examples as well. Okay. So I don't know if it helps kind of maybe print this out, kind of write down kind of next to the equations, kind of keep everything sorted. But as we kind of work through these, we'll see kind of what types of problems we'll be going to what formulas, but just kind of giving an outline there to start out. Okay. Any questions over anything or a specific formula? Okay with that? All right, so I guess now I'll field some questions. So we've got the 2 practice exams, or if you don't have a specific question or specific problem, is there just a general kind of question that you want to see kind of work through? Nobody has any preferences? Hypothesis testing stuff, older stuff. Yeah. Yeah, so I think I'll do, is this B? No, this is A. Let me do practice exam B here, because I think I have more videos up there on the YouTube playlist. So let's go down here and we'll kind of start with work through 14. Right? So let's say, and actually I'll change this one. And because if you've been working through these practice exams, you might have already seen this. And so I'm going to change this a little bit, and we're going to work through this next 4 or 5 questions. So let's say I have the same setup here, but instead I want to do instead of a known population standard deviation, let's say I was given a sample standard deviation. So first of all, I can barely read this, so I don't know if you guys can. There we go. So let's do here, we're going to change this to sample standard deviation. And, how would we write that? Well, it's simply S, right? S squared, that's our variance, sample variance. S would just be our sample standard deviation. So which of the, do I use the student T or the standard normal distribution here? So what we're going to work through won't match up with the answer key because I'm doing a slightly different problem, right? We've changed it to the sample variance. So here, what type of distribution should I use if I only have a sample standard deviation? So I've got 3 types of examples when it comes to hypothesis testing and confidence intervals. I've got a sample mean and a known population variance or a known population variance or a known population standard deviation. Anytime I'm dealing with proportions, these are situations where I use the z-table or the standard normal distribution. If I've got a sample mean, but all I have is a sample standard deviation or a sample variance, well, there I use the student t. Okay. So in this one, we only had a sample standard deviation, so we're using that student t distribution. Okay. If I then wanted to build a confidence interval at the 90% level for this, what would it be? Okay. Well, if I go to my formula sheet, here's my 3 confidence interval equations. Well, I have a sample mean, and I only have a sample standard deviation. Well, now notice in this equation is the variance, right? So I just have to be a little bit careful about how I do this. So I'm going to blow this up and we'll kind of work through this. So all I'm going to do is look at this formula and start plugging in the things that I know. Right? So I'm going to write it down so we have it as a reference, and then we'll go back to the problem. So we've got, remember, this represents the standard deviation of our sample means. So when we looked at that problem, we had what? 49 students. We find a sample mean IQ of 109. So 109 is what we're going to build our confidence interval around. I had a standard deviation of 15. So to get the variance here, I square it, right? All I had was S, right? And it's S squared. So I have to make sure I'm still squaring that 15. And then we divide by N, which our sample size here was 49. So the only thing left we have to do is look up that t-value. Okay? So we just plugged in the information we were given. Now what we need to do is for our confidence interval, look up the t-value or the number of standard deviations away we need to go to get alpha total in our tails. Now I believe that we said alpha was 0.1 here, which would correspond to what level of confidence? Yeah, 90% confidence, right? Alpha is just the outside the interval in decimal form. So that means I'm going to have half of alpha on each side. So I want 0.05 in each tail, right? But the additional thing I need with a student t-distribution is also, and the formula reminds me of this, I need to know my degrees of freedom, right? Every different sample size has follows a different student t-distribution. So that was simply n minus 1. So here, 49 minus 1 or 48. Okay. So I'm going to go to my table. I wanted 0.05 in that tail, or in each tail, I should say. So 0.05. And then I go to my degrees of freedom of 48. So 1.677. And kind of think about it, it's really positive and negative 1.677, but that's already built into our formulas, right? Adding that margin of error to get the upper bound, subtracting that margin of error to get the lower bound. Now at this point, it's just a matter of computation, right? It's just a matter, and I don't know, I wrote, oh, this was 109. So now it's just a matter of computation, right? One thing that maybe helps is doing this as an intermediate calculation. So ahead of time, right? What this really represented, oh, sorry, I had it written down here, was that standard deviation of my sample means. So maybe just do that calculation first. That way you only have one number to plug in there, right? As opposed to kind of doing it all at once. You know, I don't know, like it doesn't really help for me to kind of work through this. I don't know what the answer is. We can kind of figure it out in Excel pretty quick, just so you have something to kind of match up to. But are there any questions over that before I kind of work out to see exactly what the final answers would be here? Anything in that setup? All right, so we have 1.677 times the square root of 15 squared over, what was our sample size, 49? So there's our our lower bound. And then we'll add our margin of error. So if you work this out, right, if you get this entered into your calculator, hopefully what you're getting is about 105.4 and about 112.6. So when it comes to the exam, you'll notice like this one, oops, there we go. Usually I'll kind of go out to the second or sometimes the third decimal. So, you know, you can kind of round to the second or third decimal, whatever your answer is there. But these don't match up with what we're doing because I changed it to only having a sample variance. Any questions over this before we kind of keep moving? So question, what would change the width of this confidence interval? So if we looked at this, what are the things that would change the width of a confidence interval? So what if I see a different sample mean? What's going to happen to the width of my confidence interval? Nothing. It's just going to shift it. Right? What if I see a higher variance from my sample? Well, higher variance from my sample increases my margin of error. So we should see a wider kind of confidence interval from that. What if I want to say something with a higher level of confidence? So what happens if I want to say something with a higher level of confidence? What happens to alpha? So alpha actually gets, smaller, right? If I go from 90 to 99, alpha goes from 0.1 to 0.01. But if I want a smaller area in my tail, what's going to happen to that number of standard deviations that I need, right? Or that t-value? It's further from the mean, or it's going to get larger, right? So 1.67, the area is getting smaller, which means I need to go out a higher number of standard deviations in order to get that smaller area. So if I want to say something with a higher level of confidence, alpha is going to go down, which means that this t value is going to go up, which means what happens to my confidence interval? It gets wider. Third thing, I should have saved myself some more room, so we'll write up here. What if I take a higher sample size? What's going to happen? Well, the higher sample size decreases this fraction or decreases my standard deviation of my sample means, right? If that decreases, what happens to my margin of error? It gets smaller, so I'm going to get a more narrow kind of confidence interval there. Okay? So those three things are what changes the width of my, the first one we just said doesn't, it was just the sample mean changing. So it might be a good thing to know these, right? Wink, wink. Okay. So higher original variance on my sample, wider distribution, higher level of confidence. You know, I wrote down the steps here, but if you want to know, you know, just if I want to say something with a higher level of confidence, I need a wider range. That was the one that was intuitive, right? We don't even have to walk through the steps. We can just remember, oh, I want to say it with a high level of confidence. I have to include more values in that range, right? So I'll have a wider distribution. And then sample sizes always allow us to kind of pinpoint down better where that true population mean would be. So higher sample sizes allow us to get kind of these more narrow distributions. Any questions there? So maybe a question I might ask might look something like, you know, which of these four things makes the, you know, confidence interval wider? Which of these three things makes it more narrow, right? And then you can kind of think about which direction the different changes would have, right? I did all of these as like increases, but you know, you can imagine, what if I took a smaller sample size, or I want to say something with a lower level of confidence. All right, so now we're fine. I promise we'll get to the hypothesis testing, but I've got to setting these examples up, right? So on 16, what if we want to test for whether or not the average IQ of the Ball State student, which is what kind of, we were taking a sample of these Ball State students, and we thought, is it different from the national average of 105? So if I want to know, is it different from the national average of 105, what's my null and alternative hypothesis? Well, my alternative hypothesis is always what I want to test for, right? So here, what would that be? The true population mean is different than the national average of 105. So what sign do I need here? So be careful. In the alternative hypothesis, that's what I'm testing for. So if I want to know, is it different than 109, I actually need a not equal to sign. But you're right, what I'll assume to be true, or the null hypothesis, is the exact opposite, which is that it's exactly equal to 105. So this term of different than, automatically should be thinking, I've got a not equal to sign in the alternative hypothesis. Yeah.
So on here is H1 instead of HA.
Yeah, so on the exam, I'll always put kind of HA. The more like statistics notation is they use H0, H or H naught, H1. I always kind of put HA because it makes more sense to be the alternative hypothesis. Yeah. But H1 here, if you want to think about, it's really just referring to that alternative hypothesis. But yeah, I'll always use HA on the exam, right? So we'll make sure it's clear there. Any other questions on that before we keep moving? All right, so I've got a two-tailed test here. All right, so I can start to think about what I've got going on. So the distribution of my sample means should be normally distributed around whatever the population mean is. But we don't have a known population mean, but we've assumed it's 105. We then found a sample mean of 109. Now, before I work through this one, I think what I do, oh no, I didn't give you a new one. So we'll keep working off the same one. So on the exam, one thing that I would do here is do a reset. So like after you identify the null and alternative, I'll likely give you some different null and alternative so that we're all starting off from the same place, right? Even if you got the null and alternative hypothesis wrong, we're all kind of starting at the same place. And on the practice exam, I didn't do that because, right, you can look at the answer key, figure out what it should be, and then rework through the rest of the problems. But at this point, usually I would give you like a new assumed hypothesis test so that we're all working from the same point. But to practice exam, so we're all working from the same point on this one. So the next question is test statistic, right? What's my test statistic? So to find my test statistic, what I want to do is turn whatever sample value I found into a t-value. Now, I've got a two-tailed test here, so I should be thinking about eventually, I'm going to want to find a p-value. So I think about the probability I saw something from my sample that was as inconsistent with what I assume to be true as what I saw, or anything further or more inconsistent than that, that's going to be this area in the tail. But for a two-tailed test, I can find this area, but then what do I need to do? It's a two-tailed test. So I don't subtract from one. That's going to be, so when I'm going through the process of finding this area, if I was using the standard normal distribution, I would find the area to the left, subtract from one. Well, here with the student T, remember, it always deals with that right side. So there, I'm actually just going to be able to look up whatever that test statistic I find is. Once I find that probability, or once I find that area though, for a two-tailed test, what's the additional step? Remember, for a two-tailed test, it would have been equally as likely for me to see sample evidence on the other side that also goes against the null, right? Because now both sides would go against the null. And so I said, once I find this area, I still need to multiply it by 2 to find my p-value. With a one-tailed test, once I find the area in my one tail, I'm done. That is my p-value. But for a two-tailed test, I can find the area that's in my tail, but I have to remember, well, there's another tail on the other side that represent values that all would have also went against that null hypothesis, and it would have been equally as likely for me to see those if I couldn't only just take one sample. So we can go through the process to find that p-value, but kind of along the way, the intermediate step is to find our test statistic, or in this case, a t statistic coming from the student t distribution. So we will go to our formula sheet. Here's our test statistic equations. So at this point, it's really just a matter of plugging our values in. So our sample mean that we found, I believe, was 109. That assumed true mean is 105. And then we divide by the square root of, well, what's my sample variance? So here, remember, we were given that sample standard deviation of 15. So I still have to then square that, right? That was just S was given to me. So I still need to square it there. And then we divide by that sample size of 49, right? So I'm just plugging the values into this formula that were given to me in the problem. Any questions on that before we keep moving? Okay, so it'll be what, 15 over 7? So what does that work out to be? Oops. So we could do, what's our test statistic here? So 109 minus 105 divided by the square root. Actually, I'll do that. 15 squared divided by 49. Except for I got to get my parenthesis going the right way. So we get about 1.86 repeating. So we'll say kind of 1.87 if we round that to the second decimal. Okay. Any questions here on that setup at all? Yeah. Yeah, so all right, so now we've got our test statistic. Okay, so before we go to the p-value, are there any questions that were kind of the test statistic, and then we'll kind of move on to the p-value? Oh, you're fine, you're fine. So the sample evidence we found was 1.87 standard deviations away from that assumed true value. So to find that p-value, we have to use that student t distribution. So what I would want to do is go to this table, go to my degrees of freedom of 48, and find this test statistic of 1.87. The problem is if I try to do that, I'll notice it's not on here. Now I said I'm not going to make you put the p-value in a range for the exam. That's kind of what we would have to do in this scenario. So what I instead do is, usually at this point, give you an assumed true test statistic. Okay. So we know the test statistic is 1.87, but on the exam, at this point, I would give you an assumed true test statistic. So let me see what I'm going to do here. I'll do So let's do 2-pointer. Okay. So let's say instead on that next one, I tell you, assume that this test statistic was 1.677. Okay. So I'm going to give you a new test statistic because this one wouldn't have been a value that was exactly in the table. So now with this new test statistic, if you go to your degrees of freedom of 48, you'll see, okay, 1.677, well, that corresponded to have an area of 0.05 to the right of that. Right? So this student t distribution that kind of reminds us, it's always looking at that right tail. Okay? It kind of makes our life a little bit easier. So we've got at our test statistic, assumed true test statistic that was given to us of 1.677. The area to the right of that would be 0.05. Now, what I have to remember is that the p-value, the definition, is the probability I saw the sample evidence that I did, or sorry, sample evidence that was as inconsistent as what I found from that assumed true population mean, or anything even more inconsistent that would go against the null. The only problem is, for every value here, it would have been equally as likely we saw something that far away from the assumed true population mean on the other side. So once we find this area, we then need to multiply it by 2, or think about it as I'll have 2 areas that are both 0.05, so I would add them together, right? But they're going to be the same value every time, so I can just multiply by 2. So here, my final p-value would be 0.05 times 2, or 0.1. Okay. Are any questions over that? Is that? Okay. So with a p-value of 0.1, right? What's going to be my rejection decision? Well, if I've got a p-value of 0.1, right, my rejection decision is always going to be if that p-value is less than alpha. So I probably wouldn't give you one that works out to be this way on the exam, but this is like the hardest one, so we can at least talk through it. So my p-value was 0.1. So the benchmark kind of alphas, and I think on the exam, the way I wrote the questions, I even outlined at which of the 3 significant levels. So I say, at which of the 3 significant levels, 10, 5, and 1%, can you reject the null hypothesis? Now remember, these significance levels correspond to kind of the confidence levels, more so like how we would probably talk, right? 90, 95, 99% confidence. But I'm asking which of these significant levels can you reject? So we can think about the alphas there would be 0.1, 0.05, and 0.01. Is 0.1 less than 0.1? This is why I probably wouldn't give you this one on the exam. It's a little tricky here. But is 0.1 less than 0.1? No. So technically here, right, I'm going to fail to reject the null at the 10% level. So not quite less than 0.1. Is it less than 0.05? If it's not less than 0.1, it can't be less than 0.05, and it can't be less than here. So this would be an example where you fail to reject at every level. And these will often be options I give you on the exam. So either you reject at all levels, or maybe you fail to reject it. Or like I would say, like, you know, at what levels can you reject? So this would be none of them, right? I would fail at every single one. Yeah. But I wouldn't give you one where it works out to be like this. It would be that you would have something like, I don't know, 0.025 or something. So you could at least kind of, you know, not get tricked, you know, not trying to trick you there where they're the exact same value. So I know that I kind of deviated a little bit from that practice exam, and then I kind of try to show you like how I would set the example in terms of I'm give you an assumed true test statistic at this point, and then ask you maybe to find the p-value. What I might even do is once I ask you to find the p-value, I'll probably give you an assumed true p-value as well, right? Because if you get the p-value wrong, you might make the wrong rejection decisions. So a lot of the times, instead of continuing to use that same p-value, I might even do something like, okay, well, what if the p-value was 0.037? Okay. Well, there, I can think about comparing to my different levels of alpha. So this would be less than 0.1, so I could reject at the 10% significance level. less than 0.05, so I could reject at the 5% significance level, but not less than 0.01, so I would fail to reject at the 1% significance level. That might be more something like what I do is like pause, then give you an, assumed true p-value. Any questions related to these hypothesis testing problems? Any other questions that you want to go over, or specific questions from that practice exam? On B? Okay. So go up here. Okay. So this is generally how you'll see this set up. So a lot of the times, what we'll do at this point, I have some normally distributed variable, right? This is just kind of going all the way back to just calculating kind of the easiest z-scores, finding different probabilities. I then tell you from that normally distributed variable for 6, 7, and beyond, I take a take a sample of 29 of the students. What would the distribution look like of these sample means? Okay. Well, we should know that my sample means will always be normally distributed around whatever the population mean was. So the mean of my sample means should always be whatever that population mean was from the data that I sampled from. So here, what would that be? We're looking at monthly rent, so 460. Okay. So 460 will be the mean of my sample means. And then, let's see, does the question ask for the standard deviation of the variance? I know you asked about 7, but I'm going to, oh wait, no, you asked about 7, sorry. I thought maybe you asked about 8. So here we got 7. So we want the variance of our sample means, right? So we could look at our formula sheet, and it can also remind us that if I want the variance of my sample means, it's just the variance of the original data I sampled from divided by my sample size. So we go back here and I say, okay, what? My original variance was 10,000. So I'm going to write this down so I make sure that you can see this. So my original variance was 10,000. My sample size is 25, right? So 10,000 over 25 should be 400. Okay. So there our answer will be what? B. The only additional thing I might do here, and this is just to maybe sometimes test that I'm not trying to necessarily trip you up, but I want you to have hammered into you that if I did find the variance, if I had instead asked you for the standard deviation, what's the only other thing I need to do here? Exactly, square root of my variance, right? So I might instead ask you for the mean and the standard deviation of your sample means. Okay? So read carefully there. Okay. Does that help clarify why that is? Yeah. So right, for this problem, we really were done here, right? But if I had instead asked for the standard deviation, the only additional step is you take the square root of that variance, which if we looked at the formula sheet, you even have those formulas, right? The standard deviation of your sample means is just the square root of the variance over the sample size. Any other specific questions? So I'll show you this one since we're at this point. So at this point, I might then ask you for a probability, right? So now you're looking at a sample mean from these 25 students. So what would the probability be that you see the sample mean for monthly rent be greater than 475, but less than 500? Okay. So this kind of has a couple things that I wanted to tackle. So first of all, if it was me and I'll bring a bunch of scrap paper, I would be drawing something out for almost every problem, right? If it doesn't have to be perfect, right? Especially since you're not kind of great on your work. And so I think even if it's just quick, dirty sketches, just to keep some of the main things in focus on what you're doing, right? Or not to forget kind of easy steps. So here, I'm thinking about my sample means, and they should be normally distributed around whatever that population mean is. Right? I then ask, okay, what's the probability that I see something in between 475 and 500, right? I mean, there I'm just plotting points on this graph. automatically, what do I know has to be true about this probability? So this is one thing I would do as I'm working through the problems, just to rule out answers and not make easy mistakes. What can I say? This has to be less than. What would the area to the right of the mean be? Yeah, 0.5. So I've got something smaller than that, right? So right away, I'm ruling out C and D. I've got a 50-50 shot already, right? Now, the remaining two answers are kind of close to each other. So I guess, it's not like I can pick out which one, but at least like I'm ruling out some of these extreme values. I'm preventing myself from making some mistakes. And we can see why I make those mistakes as we work through this, okay? So the first thing I'm going to do is I need to turn these values into z-scores. So if I go to my formula sheet, I go up here, I'm dealing with a sample mean distribution. When I want to turn these into z-values, I'm going to use this equation right here. So for this first one, that would be what? 475 minus the population mean of 460 divided by the square root of, I didn't leave myself a lot of room here, but it's going to be the original variance over my sample size. Well, another thing I can kind of think about, if I had done this ahead of time, and this should be what, I think 20. Really what's in this denominator here is the standard deviation of my sample means. So if I already have that calculated, I could actually just plug in one value. Now, if that kind of gets too confusing, I can just go ahead and plug in those values of 10,000 and 25. I can just plug those values in there. But really all I'm trying to do is turn this into a z-value. So I think what this is, am I thinking this right? So 20, so the difference there is 15. So 15 over 20 is 0.75. So 0.75 is that z-value. I'll blow this up here real quick. All right, that's that z-value here. If I do the next one, right, just for the sake of time, I'm basically doing the exact same thing, but I'm plugging in 500 as the sample mean value I'm interested in. If I do that, I believe I get a z-value of 2, right? So 500 minus 475 over square root of 10,000 over sample size of 25. That's how I got that z-value of 2 there. Because I was going too fast. yeah, I should be subtracting that part. Sorry, I mixed my numbers up there as we were. Yeah, right. I'd always be subtracting that true population mean. Thank you for saying something. Any questions at that point? So I'm going to give myself a little more room here. So I'm just going to redraw this for us to kind of clean it up a little bit. So we just had these z values of 0.75 and 2. And we're looking for that area in between. So what I'm going to do is if I look this up, right, and this was an example where we have this known population variance, right? That was coming from problem 5. So I can use that z table, look up the area to the left of a z-score of 0.75, look up the area to the left for that z-score of 2, and then what's the final step I would have to do? Subtract that smaller from the larger area. Right? So I'm just going to go ahead and do that here real quick. We'll go to our z tables. So I want 0.75, so 0.7, oh, I have to move this a little bit, 5 here. 0.7734. So this smaller area, 0.7734. Then if I look up that z-value of 2, 2.00, 0.9772. And now at this point, I just have to subtract that smaller area from that larger area. I get what, 0.20. So maybe I add in on the exam, maybe 2 questions. So maybe I'll, what's the probability that I'm just below a certain sample mean value? And then maybe the second question is what's the probability I'm in between 2 values? like I said, drawing it out can always kind of help us, prevent us from making mistakes. One thing to always kind of pay attention to is if I ever do ask, for something like, so here is our mean, here is our sample mean distribution. What if I, wanted the probability that it's greater than 440? Well, I go through the same process, but once I turn this into a z-value, whatever that z-value is, when I look it up in the table, I'm going to get the area to the left. So there, if I'm looking for the probability it's greater than something, what's my one last step that I would then need to do? So this is what the table gives me. I want the area to the right, so yeah, 1 minus that. And that's the same kind of deal when it comes to hypothesis testing, when you're doing right-tailed tests, right? Once you get your test statistic, you can go to the table, but the table for that standard normal distribution always tells you the area to the left. So if you have a right-tailed test, you want the area to the right, so you still have to subtract it from 1. Okay. I think the one-tailed tests are easier just because, especially left-tail, because for left-tailed test, I'm thinking about finding my p-value. Well, once I calculate, whether it's a z or a t statistic, right? No matter what the example is, if I have this negative z value, I go look it up in the table, it tells me the area to the left, that is my p-value, right? For a left-tailed test, it's the probability I saw something as many standard deviations below the assumed true value or anything to the left. For a right-tailed test, this was left. For our right-tailed test, remember, once we found our z-value, our p-value is actually the area to the right. So if I'm using that standard normal table, it always gives me the area to the left. For a right-tailed test, I'm going to have to subtract that from 1 because I'm looking for the area in that right tail. And how did we identify the type of test that we had? What do we always look at? The alternative hypothesis, right? So if I'm looking at down here, if I'm looking at something like 10, what did I want? I wanted to know if it's greater than 36% or as a proportion, right, greater than 0.36. So here I want to know, is that true population portion greater than 0.36? I assume the opposite is true. So here, what type of tailed test would I have? Yeah, so what'd you do? You looked at the sign in the alternative hypothesis, right? So I go to that alternative hypothesis. I've got that this population portion is greater than a certain value, right? So I have a greater than or a right-tailed test. Okay. Let's see, do I have any other examples here? Let's go to practice exam A just so we can go through a few here real quick. Let me see. Where are you at? Okay, so here, you want to test for whether or not that population portion is different than 45% or as a proportion different than 0.45. So I see this term different than, this one should be pretty easy. What's the answer for 11? I want to know, is it different than 45% or a proportion of 0.45? What should I be thinking about as my alternative hypothesis? Yeah, so different than is not equal to, right? So anytime I see this term different than when it comes to hypothesis testing, two-tailed test. What's a two-tailed test? Well, that's when I have this not equal to sign, right? Not equal to or two-tailed test. So this one, it's not like I even tried to necessarily confuse you. There was only one answer that even had the equals and not equal to sign there. So, hopefully I would look back through, look at the ones in the practice exams. But if you're struggling with identifying the normal alternative hypothesis, go back to the slides because I can guarantee there's going to be at least 2 on the exam. And I think that those should be some of the easier ones, right? Like you're really just, it's just deciphering the kind of way the problem reads it to you. And like I said, this term of different than, right? Like two-tailed test every single time. Okay. So here I've got a, what type of tail test? I think I've already said it, but a not equal to or a two-tailed test. So this would be one where once you find that area that's more extreme than your test statistic, right? So for a left-tailed test, that was the area to the left. Right-tailed test, that's the area to the right. But if it was a two-tailed test, once I find one of those areas, I have to remember, like I might only see my sample evidence is above that assumed true mean, but I have to remember for a two-tailed test, it was equally as likely for me to see something on the other side. So once I have the area, I still need to multiply by 2 to get my p-value. Yeah.
So the problem we did first had the
Mm-hmm.
109.
Yep.
What did it say for that one? Did it say that one was also?
Yeah, so if we go up here, where was it? Yeah, so I want to test for whether or not the average IQ is different than the national average. Yep. Yeah, anytime you see this different than, two-tailed test. And then there should have one more example over here. Here we go. So we want to test for whether or not the average dental salary is less than this reported amount, right? So if I want to test for whether or not the true salary is less than this 150,000, the reported amount, I should be thinking about what I'm testing for. That's my alternative hypothesis. So the way that these questions read, whatever you read in words, that should be your alternative hypothesis. You want to test for whether or not it's less than 150,000. So your alternative hypothesis is it less than 150,000. Then once you have that, identifying the null is just the complement of that, right? Or the exact opposite. So here, what type of tailed test would I have? Yeah, I got a less than sign in the alternative hypothesis. So I have this left-tailed test. And like I said, I'll just ignore all these critical value questions on the practice. Is there anything that I want to think about? And if you're going through these, don't worry about question 20. What we've talked about, you could probably answer this one. But since we don't have as much familiarity, I probably won't push you as far as what this question would be, which is starting to think about how does the sample size influence kind of the outcome of our hypothesis test. But we'll kind of hold off on that. So wouldn't worry too much about 20 here either, but the rest of these are fair game. Okay. Any other specific questions for me or questions related to the exam? So let me think if there's any other last minute tips I have. So I would really focus on the examples, kind of like the one I worked through today. There's probably a reason why I changed it to a sample standard deviation or a sample variance. So I would kind of pay attention to that practice exam that had the hypothesis test where you only had a sample variance, maybe a little bit more than the other. I would also really kind of go through, and since you have 2 examples on both practice exams, think about how you do confidence intervals and hypothesis testing with proportions. Okay. One thing on there that can sometimes trip people up when we're looking at this test statistic equation, remember what you're using in the denominator. That's going to be the assumed true proportion. So that's not what you found from your sample in the denominator there. That's going to be the value that's coming from your known alternative hypothesis. Okay. So that would be one mistake that to be careful of on those problems, and maybe focus on looking at the hypothesis for those problems as well. Other than that, there's no more questions for me. So I will be in my office 2 to 4 today, as usual. Tomorrow, 3:30 to 4:30. If you have any last minute questions, if you want to meet sometime tomorrow afternoon, I do have a class, but earlier in the afternoon, we'll probably set up a time. Feel free to send me an email. Other than that, like I said, I'll be here a little bit early so we can get kind of going. It'll be kind of same procedure as the last exam. I'll hand out the exam that'll have the student T, standard normal, and the formula sheet. That'll be like all stapled together. And then I'll kind of have blank paper to hand around afterwards, but we can kind of get going right on time. Okay. All right. Good luck with studying, and I will see you guys on Wednesday.